Right, this is Unit 1, Day 3. We're going to be talking about radical functions and their graphs. Specifically, today we're going to be looking at square root functions. First of all, I just want you to remember way back to Math 2 last year, you learned how to graph parabolas, these quadratic equations. So this first one I want to graph as a reminder from last year is f of x is equal to x squared. So if you remember back, that is a parabola. This is just a basic parabola. It has a vertex at the origin, the point 0, 0. So the origin is right here. And then last year in Math 2, your teachers taught you the pattern 1, 3, 5 to graph these parabolas. So from that vertex, you go up 1 over 1, up 3 over 1, up 1, 2, 3, 4, 5 over 1. And then, of course, the other half of the parabola looks exactly the same. And it has this U shape. This second function, g of x, is also a quadratic. It's going to be a parabola, but it has some transformations happening. So the vertex of the second one, you might remember from last year, is at 1, 3. So remember that in the horizontal direction, that x minus 1 changes to a 1. It goes to the right 1 and up 3. So the vertex is here. And if we use that same pattern, 1, 3, and the 5 goes off the graph, so we just will have these points. And, whoa, I kind of missed. Here's our parabola. So last time we started talking about inverses, and we talked about that inverses switch the x and y, and they reflect the function over the line y equals x. So I want you to think about what the inverse of these parabolas would look like if we reflected it over a diagonal line like this. And that's kind of hard to picture. Here is what it would look like. This is the function f of x equals x squared. And this blue graph shows the inverse relation. It shows that reflection. But this blue graph is not a function. And the reason that it is not a function, if you think back to prior math classes, is that it would fail the vertical line test. For some of its x values, like 5 for example, it has 2 output values that go with that input, so it is not a true function. Well, if we have a function and we want its inverse, there is a way we could get it to be a function, and that is if we limit our parabola to just half of that parabola instead of the whole thing. And we can tell, or we can state that it's only half a parabola by putting this little domain restriction. So this is saying our function is f, it's the equation x squared, but we're only going to consider the x's that are greater than 0. I should have a 0 here. So we're limiting it to half of the parabola. If we do that, then the inverse, the reflection, it is a function because it doesn't have that lower half. So now it does pass the vertical line test, and both the function and the inverse relation are functions. So let's look at algebraically how we can find this inverse. We can see what it looks like there, but let's do the algebra. So our question is, what is the inverse of the function f of x equals x squared? So in other words, I'm wondering, what is the equation of this blue graph? How could I write that as an equation? Now this part of it, if you remember from the last slide, it's just a domain restriction. It's just telling us that it's only half a parabola. So when we're finding the inverse algebraically, we don't use that information as we're finding the inverse function. We just have to know that it's only half of a parabola in order for the inverse function to actually be a function. So we're going to follow exactly the same procedure that we followed last time to find an inverse function, and that is that we're going to switch x and y, and then we're going to solve for y. So our function right now is y equals x squared. This is our y value. And remember, we don't have to use this restriction. It's not necessary for the algebra here. It's just necessary for us to know that it's half a parabola. So we're going to switch the x and y. So this becomes x equals y squared. Now they're switched. And now our goal is to solve for y to find that inverse function. Well, the only thing that's happening to y is that it's being squared. So if I want to undo that, I need to take the square root of both sides of the equation. Once we take that square root, on the left side we have the square root of x, and on the right side that reduces to just y. The squaring and the square root sort of undo each other. And so this is our inverse function. F inverse of x is equal to the square root of x. Here's our inverse. So for the function f of x equals x squared, the inverse function is f inverse of x is the square root of x. Let's try another one of those, a little bit more complicated. So this time we have x minus 1 quantity squared plus 3. And this end part, remember, it's just a domain restriction. So it's not necessary for us to use that in the algebra here. So we're going to remember that g of x is the y value. And we're going to switch the x and the y so that we can find the inverse function. And now to get that inverse function into standard form, we just need to solve for y. So in this case, we would subtract 3. That gives us x minus 3 on the left, and on the right, we have y minus 1 quantity squared. And we're still just working towards getting that y by itself. So right now, it's a y minus 1 all being squared, so we can take the square root of both sides. So now we have root x minus 3 equals, and again, the squaring and the rooting undo each other, so we're left with y minus 1. And we're almost there. We just want to get the y by itself, so we're going to add 1 to both sides. Now this is tricky. When we add 1 on this right side, it's happening after we've already finished taking the square root. So it's actually not going to combine with that negative 3 in any way. The square root ends, and then we add 1. And we've done it. We've gotten the y by itself, so this is our inverse function. In this case, g inverse of x is equal to the square root of x minus 3, and that ends the root, and then plus 1. This is just showing you what those functions and the inverses that we just found equal, so or look like. Here is our original function x squared. It shows half of the parabola because of the domain restriction. The inverse of that, which on the graph looks like a reflection, that's the function square root x. And over for g of x in this case was x minus 1 squared plus 3, had a domain restriction that restricted it to just half of that parabola, and the inverse of that, which we just found, is the square root of 3, the square root of x minus 3 plus 1. So that's just showing you a visual of those two that we just calculated. Let's try one more inverse, and then we'll move on to some more graphs. I want to know what the inverse of h of x is equal to the square root of the quantity x plus 5. So again, same process. Doesn't matter what function we're dealing with, we can use this process. We have to remember that h of x is our y value. We're going to switch the x and the y. So this becomes an x. We'll have a y over here. Everything else in the equation stays exactly the same, just the x and y switch. And now to get that inverse into standard form, we'll just solve for y. In this case, we have a square root that is on that left-hand side. So we need to square both sides of our equation. So on the right, on the left, we have x squared, and then on the right, the squaring and the square root cancel each other out. They undo each other, and so we just have y plus 5. Again, we're trying to get y by itself. So to finish that up, we can just subtract 5. So we have x squared minus 5 is equal to y, and this is our inverse function. In this case, the original function was h, so the inverse is h inverse equals x squared minus 5. So here's the inverse function. So you can see if you start with a square root, your inverse is actually a parabola. All right, so now let's switch gears a little bit. We're going to focus now on graphing the square root function. It's going to work a lot the same way as parabolas and absolute values worked, and you're familiar with those from last year. So the square root function is going to behave the same way. We're going to talk about 3 different transformations, 1, 2, 3, and then we'll do a couple of graphs that combine transformations. So our first transformation is what happens when we add a number to our function. Well, our function that we're focusing on today is a square root function. So in particular, we want to see what happens if we take the square root of x, that's our function, and we add 3 to it. So you can use a calculator to fill in this table since we kind of know what this shape looks like, but I want to use a table of values to graph it the first couple of times. If you plug -1 into this equation for x, and type it into your calculator, type, you should get a big fat error. It doesn't work. Because when you try to take the square root of a negative number like -1, it is, you might remember, imaginary, but we're trying to make a real graph. So we are going to say that that square root doesn't work because we aren't going to work in the world of complex numbers today. Your calculator said error. If you put in 0 into this equation, square root of 0 plus 3, you could use your calculator to find out that that's 3. And if you kept going and pushed these into your calculator, you would continue to get the rest of the table filled in. If you were in class right now, I would make you type all of those in. So let's plot these points that we've just found. -1 was an error. That means that it's not part of the domain of this equation. There is no point to plot for that first row. The point 0, 3. Oh, haha, sorry. 0, 3. I know how to graph. 1, 4. And, you know, these two came out to be decimals. You could try to get them in approximately the right spot. But I'm just going to go down to here, 4, 5. 1, 2, 3, 4, up 5, 1, 2, 3, 4, 5. So this is what the equation y equals square root of x plus 3 looks like. Anytime you have a number added to the end, if it's a positive number or a negative number, that represents a vertical translation. Adding a number at the end of the function is shifting it up and down. In this case, we shifted up 3. Let's write the domain and range of this function. So in interval notation, it specifies. So the domain of this function, left to right, would be from 0 to infinity. Starts at 0. And the range would be bottoms up, so the lowest value is 3 up to infinity. All right, so we are done with our first type of transformation. That was a vertical transformation. Next kind, what happens if you have a number added to x within that function? So again, we're working with a square root function. So we're talking about the equation y equals the square root of, and we want to add 2 to x. So both the x and the plus 2 are under the radical. So if we fill in the table of values, crunching those numbers, once again you get an error for that first one. If we put -3 in, we end up with the square root of -1, which does not compute. And if we keep crunching those numbers, we get something like this. So let's plot those points. -2, 0, -1, 1, 0, it's like 1.4, 1, 1.7, and 2, 2. So here's our function. And you can see that it has that same shape, but this time instead of shifting up or down, it shifted back to the left. This is a horizontal translation. Anytime that number is being added to the x, in this case under the radical. So let's write the domain and range of this. This time we are using inequality notation. So the domain, well, it looks like this function is just fine as long as x is greater than or equal to, it looks like the smallest it could be is a -2. -3 gave us an error, so we have to have numbers that are greater than -2 for our domain. And the range, this is a y value, remember. The y is going to be, in this case, the very lowest value is here at 0, so the y has to be greater than or equal to 0. So there's the domain and the range of that. All right, so that's our second transformation. One more type of transformation. What happens if we have a constant, some kind of number, and we multiply our function by that number? So instead of adding, we're timesing. Remember, our function is the square root of x. So we are talking about an equation that might look something like 2 times the square root of x. So once again, we can fill in the table. We plug in -1, and it's an error. Here we should get 0, 2, and you should crunch these numbers, see if it works for you. 4 and 6. So I'm going to plot those points. 0, 0. Again, that first one, that error, it's not on the graph. 4, 4, and 9, 6. Did you catch that I changed the x's on this table? I didn't just go 1, 2, 3. All right, so here are our points. And the graph is a little different from the prior ones. A regular old square root of x would look like this. That's square root of x. And what we've just graphed is that square root of x times 2. So maybe you can see from those two pictures that what that 2 is doing in this case is stretching it. Multiplying by a number represents a vertical stretch. And let's write the domain of this. I'm gonna move the red one just so we don't get confused by it. So the domain of this function 2 times the square root of x, we're writing it in interval notation again. So it looks like from left to right, it's 0 to infinity. And the range from bottom to top, bottoms up, is 0 to infinity. 0 is the lowest value. Okay, so just 2 graphs left to do. We just went through the 3 different types of transformations, and now we're just going to combine them. So we might have a stretch. We might have some kind of left or right movement, and we might have an up or down movement. with our graph. And we'll have a vertex. It's not really a vertex, but maybe you would call it a starting point for a square root at HK. Now, the three graphs that we just did, we used a table of values to help us plot those points. I don't know about you, but I would much rather use a pattern to help me graph. So in the past, when we taught you to graph quadratics like x squared, we used a pattern to help us. We started at our vertex, we went up 1 over 1, up 3 over 1, up 5 over 1, 1, 3, 5. And when we used that pattern, it gave us that nice parabola shape. Well, we can use that same pattern here. The graph of a radical square root function has that same pattern in it. It's just that the shape of the square root is slightly different. It's reflected over that diagonal line. So it's instead of a vertical 1, 3, 5 pattern, we do it sideways. So we go up 1 over 1, up 1 over 3, and up 1 over 5. And you can see that when you do that pattern, it creates this sideways parabola that is a square root function. So it's a 1, 3, 5 sideways pattern. We'll use that pattern instead of a table of values because it makes our graphs quicker and usually more accurate. So our first function, f of x equals the square root of x minus 1 minus 2. We've got a minus 1 inside the radical, and we've got a minus 2 outside that radical. So what we want to do is find the starting point, kind of like you used to find the vertex. Starts at, and in this case, it's going to be a 1. Remember, we changed the sign of the one that's with the x. It's shifting it the opposite of what we might think. So it's a minus 1, so it's going to go forward to the right 1. And that negative 2 is going to stay negative. So it starts at this point 1, negative 2. Here it is on the graph right here. And then we can use our pattern. From this starting point, we can go up 1 over 1, up 1 over 3, up 1 over 5. And there's our function. So let's use interval notation to write the domain and range. The domain, we're using intervals, so from left to right is 1 to infinity. And the range, bottoms up, lowest value is negative 2 up to infinity. These do get square brackets for radical functions because it does include that point on the end. Last one. Graph the function g of x equals 1 minus 2 times the square root of x plus 4. This one looks a little bit different from the other ones we looked at, but don't panic. It's really very similar. It's just written in a weird order. Remember, if you have 5 plus 3, that's the same as 3 plus 5. It doesn't matter what order that we add things in, it's the same total. Well, in this case, they put that radical second, but we could put it first. And then they put the 1 first, but it's the same thing if it's second. Same sum, it doesn't matter which order. So this one was written, I guess you might say backwards, but sometimes things get written that way. It's not uncommon. So now that we have written it in a way that maybe looks more familiar, we can find our starting point. This one happens to start at the point negative 4. Remember, that comes from this positive 4, but we change the sign of that one, and positive 1 from the plus 1 at the end. Negative 4 plus 1. Here's our starting point. Now we have a minus 2 in front of our radical. That is the vertical stretch. So instead of going up 1 each time, we're going to go down 2. Now this is a little bit different from parabolas. You might remember when the parabolas got stretched, it multiplied that pattern, so it became, instead of 1, 3, 5, 2, 6, 10. But in this case, the stretch is stretching downwards, so we go down to, whoops, sorry, I shouldn't have put a point there because I should talk about going over. Down 2 over 1, down 2 over 3, down 2 over 5. The 1, 3, 5 stays because the 1, 3, 5 is in the horizontal direction. It's the going up or down that changed. So the function started at -4, 1. Our pattern here was down 2 over 1, down 2 over 3, down 2 over 5. And now we're going to write the domain and range of this function in inequality notation. So the domain here, if we're looking at the x values, it looks like all of the x values of this function are larger than or greater than or equal to -4. And for the range, this one's a little different. Instead of having the y values greater than a number, our y values can be very negative. They have a highest value that they can't go above, so it's y is less than or equal to, in this case, +1. If we wrote those in interval notation, it would look like -4 to infinity, and if we go bottoms up here, -infinity up to 1. So it's a little bit different than the prior one. And that's it. So that's how to graph these square root functions. The homework assignment on the answer key on the homework assignment paper, my bad, I changed some of the problems around and rearranged it a little bit, and I didn't fix the answers. So please disregard the answer key on this assignment because some of the answers don't match up with the questions. Really, really sorry about that. So that's it this time for graphing square root functions. Next time we will be graphing cube root functions. So this is exciting stuff. Thank you.